Hello and welcome back. Today we're going to be talking about pulleys in the context of Physics 1. Pulleys are a type of simple machine. It helps redirect forces to accommodate easier functions of lifting, pulling, and many other things. Now, if you're like me and you're extremely buff and huge and muscular, I'm just kidding, I'm really short and underweight, you know that the tension in most cables is made via pulleys. You can see in this simple diagram 1, 2, 3, 4 on the other side, 5, 6, 7, 8, 9, 10, 11, 12 pulleys just for this simple cable pull down machine. And that's so that when you're pulling down on a chunk of weight, it helps redirect so that when you pull down, whatever weight you're pulling goes up. It's a simple redirection of force. Now, unlike pulleys in a classic physics problem, pulleys in real life are not perfect. They have mass, they have friction between the wheel and the cable itself, so each pulley adds a little bit of work. And you'll notice that if you use two different types of the same machine, let's say you're doing a cable fly and you're doing 45 pounds, but on another machine you can do 65 pounds. This is all because of the pulleys either degrading in quality or just as they were built not being as ideal as the other machine. So pulleys are used in a lot of things besides exercise machines, but for Physics 1, we're first going to take a look at massless and frictionless pulleys. If we go back to this diagram here, that means that in this entire system, this wheel here, which is what a pulley is made out of, doesn't have any mass, and also between the wheel and the cable here, all around where they're touching, there is no friction, so you don't need to worry about that when doing your Newton's second law equations and whatnot. And that's really helpful because it's a good way to approximate accelerations, mass, whatever. Let's check out a really basic problem of a man holding a mass over a pulley. This awesome looking man right here is holding up this weight of mass, capital M. Now, this pulley is massless and frictionless. In Physics 1, your teacher or your tests or your AP exams, whatever, will probably say a massless, frictionless pulley. In case it doesn't, however, if there's no information given like the coefficient of kinetic friction or something like that, you can assume that the pulley is massless and frictionless. Usually if it's not that, the problem will outright state there is friction between the cable and the pulley, or there is a mass for the pulley. Otherwise, you can pretty much ignore all of that. Now, without any values here, I want to try analyzing this situation. We've got Mr. Man McGee over here carrying a weight, and I'm going to make an FBD. This red FBD is going to represent the dude. So what forces are acting on the dude? Well, it's not said, but we're on Earth, alright? You don't need to have that specifically stated. So we've got a force of gravity, Fg. Now, this dude is not accelerating into the ground, right? I hope not. That would be quite bad if that were to happen. So there must be a vertical force disengaging the force of gravity from pulling this man into the center of the Earth to burn alive. And as I've said in previous videos, that is called the force normal, Fn. That is the force acting from the ground onto the dude. So like pointing up through him. And because the dude is not accelerating in either up or down directions, these must be equal. These little dash marks I make on the arrows just represent they're of equal length, because I am not amazing at drawing, so they might be a little skewed in terms of length and size. Just know if there's a dash, they're equal. And if there's multiple pairs that you want to show are equal, you can just add 2 dashes, add 3 dashes, add 4 dashes for how many other pairs you have. Now, there's more forces acting on this man. This dude is holding a mass. He's holding it with his hands, right? So there must be something from his hands pulling on him. There must be a force pulling on the man. And there is. And we call that Ft, aka the force of tension. Now, why is it called the force of tension? Let's look at a rope. This is a rope with 2 ends, right? If someone were on this side pulling to the left, and someone were on the other side pulling to the right, what is going to happen to this rope? Assuming it's not an elastic rubber band type, and it's going to stay the same length. Well, the rope is going to start fraying. It's going to start breaking. There's something about this situation that is making the rope tear, basically. And we call that the force of tension on the rope. If a rope is pulled in any way, that rope is in tension. So, if we look at this pulley system again, is this rope that I'm circling here in tension? Yes, it is. The mass here is pulling downwards on the rope, and the dude is trying not to accelerate to the right. He's trying not to fly forward, so he is holding the tension that way. Now, you might be looking at my diagram right now and go, now hold on a second. Why is this arrow pointing to the left, but on your FPD, your force of tension is pointing to the right? And that's a great question. The answer to that is that an FPD is the forces acting upon the subject. And in this case, the subject is the man. So let's go back to our previous forces. The force of gravity is pushing the man down. The force normal is pushing the man up. So what is the rope doing if the mass is pulling downward? The rope is trying to pull the dude to the right. So you can use your intuition to kind of tell what way the rope is pulling whatever subject you're working with if it's in tension. So let me get rid of all these really ugly looking arrows everywhere. And from that, you can kind of use your intuition to tell that the rope is pulling the man to the right. So in this scenario, there is no friction between the dude and the floor, which means, unfortunately, Mr. Man is about to go flying to the right. Before we do some analysis on that, I want to make an FPD for the mass itself, the mass big M. This one is somewhat simpler. Now, there is a force, Fg, correct, going down. So, what other force is acting on this mass M? Well, just like the guy, there's a rope in tension attached to the mass. So there must be a tension force pulling upward on the mass. Now, that's all fine and good, but what can we actually tell about this system here? Well, what if I were to tell you that the force of tension on the big M is equal to the force of tension pulling on the guy, because that is true with a massless and frictionless pulley specifically. Like I said in the beginning of this video, the whole purpose of a pulley is to redirect force to better accommodate people, basically. So instead of having to pull this mass directly upward, Mr. Man can redirect that force to the left via the pulley. Now, if this rope just extended this way, the force of tension wouldn't change, correct? If you're looking at this logically, why would the force of tension change at all? So, in a pulley, once again, why would the force of tension change? And the answer is it doesn't. There is a force of tension that goes this way, Ft, and a force of tension that goes this way, and they are exactly the same. And that's really, really, really cool. So let's do some small amount of math here just to see how this all plays out mathematically. And let's say I'm trying to find the acceleration of Mr. Man here. So we've been given a scenario here where there's no friction between the floor and the feet of Mr. Man. So right now, F net, not the same as Fn. I've seen people make this mistake a lot. Fn is not the same as F net. Fn is the force normal. F net is the net force on the subject. Okay, cool. F net of the man, I'm going to write it in red to match the FBD. F net is equal to Ft. Now, why do I say that? I say that because Fn and Fg cancel each other out. There is no net force in the vertical direction because, yes, there's an upward force, yes, there's a downward force, but they cancel. So really, there is no force. There is, however, a force to the right, the force tension. Okay, cool. Let's go to the big block mass. F net of the mass is going to be Ft minus Fg. Now, if you're like me, I don't really like that. And why is that? Okay, realistically, and through the definitions I have set up via this system here, this man is about to go flying to the right. He's about to experience Superman flight. If he is going to the right, what does that mean for the block? It means the block is about to go down, right? Which kind of makes it annoying that Ft minus Fg must be negative. Now, why is that? It's because F net is going down, and just standard notation, up is positive. So I'm going to do something a little silly, and it's something I've done in previous videos about changing coordinate axes. I'm going to say that down is actually the positive direction. So F net is now Fg minus Ft. So now we have two equations based off Newton's second law, and we can kind of use those to find the acceleration of Mr. Man. So let's write those down. We have F net equals Ft, and we have F net of the block equals Fg minus Ft. I know my handwriting is pretty bad, but I'm saying it out loud, so hopefully you can kind of follow along with what I'm writing down. So F net is equal to ma, right? That is Newton's second law. And let's say the mass of Mr. Man is little m. Cool. So we can say ma is equal to Ft. And the m here is tiny m, not big M. Big M is the block. And we can do the same thing for the block. we can say big MA equals FG minus FT. Now, that should all make sense, but you may have overlooked that I did something pretty huge here. I did something monumental, all right? I made this A and this A equal. Now, maybe if you're thinking about this intuitively, you might say, well, yeah, obviously, Mr. Man goes right, block goes down, they're both accelerating, but really, their accelerations being the same is kind of an amazing thing that comes about by using frictionless and massless pulleys. This is an assumption we can only make with frictionless and massless pulleys, that the acceleration, if a pulley is in use, of the items on both ends of the cable of the pulley are accelerating at equal rates. Now, if you've watched my acceleration video, you know acceleration is a vector. So, are they truly equal? No, not really, because the vector of Mr. Man is going to the right and the vector of the block is going down, and by vector I mean acceleration vectors. So, if you really want to think about it, no, they're not entirely equal, but for the purposes of Newton's second law and the equations thus, we can kind of arbitrarily say that they're equal. Because we're only worried about the magnitude of the vector here, not direction. So really, this A is absolute value. Nope, it's not absolute value. This A is the magnitude of the vector A. It's not the vector A. If it was the vector A, it would have a cute little hat, but it doesn't. So let's treat A as the magnitude. And you're going to want to think about that because most people don't. I'll be honest. Being in tons and tons of physics classes, you tend to see people just use A and move on with their life. But if you really think about it, it gives a better understanding to how all of this works. It's just something to keep in mind. So let's keep going on the math. We now have little ma equals ft, big ma equals fg minus ft. Now, fg is something that we can find. As you have probably seen from an earlier video or just in your life, fg is equal to mg, mass times acceleration due to gravity. So we can say that big ma equals big mg minus ft. So right now, we have two equations, right? We have equation 1, equation 2. How many unknowns do we have? Let's list them. We have unknown, we don't know the acceleration, and we don't know ft, force of tension. However, that's two unknown variables with two equations. We can actually pretty easily find what these values are. So let's do that. I'm going to erase this list here. If we plug in ma equals ft into equation 2, we end up with big ma equals big mg minus little ma. If we reorder this around, we have big ma plus little ma equals mg, big mg, sorry. And once again, reordering, we have m, big M plus little m, all times a equals mg, which gives us a equals big mg over big M plus little m. And this right here is our acceleration of both the block and the man. And this is the magnitude, not necessarily the direction, but we know the mass of the block, we know the mass of the man, we obviously know g, it's 9.81 meters per second squared, so acceleration has been found. Now what about the other unknown, ft? Well, that's quite easy. Equation 1 is simply ma equals ft. if we just go Ft equals m and plug in our a value, big M plus little m, I'm going to make this big M more obvious that it's big M. Big M. There we go. Ft is found. Congratulations. Pretty cool, right? We've done, without any numbers, we've found a pretty good estimation for acceleration and the force tension of a completely arbitrary pulley system. And if you're like me, and you like physics, and you're a nerd, this is really, really, really cool. Before I end this video, we're going to do this exact same example, but just tweaking it a little bit. So this time, I'm going to say that there is friction between the floor and the man's feet, force Ff. And I'm also going to say that the man, Mr. Man, and the block are not accelerating. So either they're just sitting in place, or they're moving at a constant velocity. Let's set up the same FBDs we did before, but now taking into account force of friction. So the man's force diagram is going to be the same Fn, Fg, Ft, but we have to add force friction going left. Now why is it going left? Well, it's to counteract the force tension. And if you're thinking about this intuitively, and you notice that if the man is going right, friction must go to the left. So in this case, it doesn't matter if it's kinetic or static friction because acceleration is 0 and we don't have any numbers. So we can just say that the force of friction and the force of tension are equal and opposites, which means A is 0 of this man system. And the FBD of the block is also quite similar, where we have Fg and Ft. But like I said, acceleration must be 0, so there must be no F net, which means Ft here is equal to the Fg of the block. Now, just like I said before, I want to try and find the two unknowns here, acceleration and the force tension. Now, just by the definition of the problem I have set up, acceleration 0. I've been saying this. It's obvious. Hallelujah, right? So then what is Ft? Well, let's take a look. In our FBD of the big block, we clearly see that Ft is equal to Fg. Now, we know what Fg is of the block. It's Ft equals big Mg. And I think we've done it. This is it, right here. Pretty cool, right? Now, that's not the only way to do this. I'm going to do this via the man's FBD, but it's really not needed. It's quite as simple as F net equals ma. Pretty simple. But I am going to do this again via the man's FBD. From the man's FBD, we can see that Ft is equal to Ff. Now, if you remember from the force friction video, Ff is equal to Fn mu, and mu is the coefficient of friction, in this case, static or kinetic. And we know Fn is equal to Fg, so Ff is equal to little mg mu, which means Ft is equal to little mg mu. And once again, we've done it. We've found Ft. You can probably see here how making acceleration 0 makes pretty much every problem easier. So here we have two different ways of finding Ft. And this is hinting that in future problems, there might be several ways to get the same answer. But that's for the future. Well, that's it for me on pulleys. I've given you a brief introduction to how pulleys work and how they're used in physics problems. We didn't even have to use numbers to be able to get our answers here. We've done this completely symbolically which I suggest you do for all of your problems and then just plug numbers in. Trust me, trust me, trust me. It makes everything a lot easier to handle. So, that's it for me. Thank you for watching and happy learning.